Assalamualaikum. Hi everyone. So this is chapter 2, Thermochemistry. In this video, we're going to look on the subtopic of 2.2 calorimetry, and at the end of this lesson, you should be able to first calculate the heat change in a constant volume calorimeter, which is we also call as bomb calorimeter, and then calculate the heat change in a constant pressure calorimeter. So now, let's take a look. So the first one, before we enter the calculation, we're going to look first on what is calorimetry and what is calorimeter. Calorimetry is the measurement of heat flows, and the understanding of the heat change will depend on an understanding of first the heat capacity and second the specific heat capacity. For these two terms, the heat capacity and specific heat capacity, is already been discussed in our previous video. Okay, here I will give you the equation related to the heat capacity and specific heat capacity just to refresh back your memory. So the equation involved for heat capacity is Q equals to heat capacity of our substance and then the change in temperature delta T. Okay, for the specific heat capacity, so Q represent the heat mass of the substance, and then its specific heat capacity, which is our capital C, and also delta T. So this will be the two equations that we will use in our calculation later. So next is calorimeter. So calorimeter is the device used to measure the heat released or absorbed by a physical or chemical process. Okay, for your syllabus, we have two types of calorimeter that we're going to use, which is the first one is constant volume calorimeter and the second one is constant pressure calorimeter. For the constant volume calorimeter, we also call it as bomb calorimeter. Okay, so this bomb calorimeter is used for combustion. Okay, and then for constant pressure calorimeter, we also call it as the simple calorimeter. Okay, and usually this simple calorimeter is used to determine the heat of neutralization reaction. Now, let's take a look one by one. We're going to look first on the constant volume calorimeter. Okay, the constant volume calorimeter, or like I said before, we call it also as the bomb calorimeter. So, how does the bomb calorimeter looks like? Okay, first, it is used to determine the heat change for combustion reaction. So, anything that goes with burning something, okay, and we want to determine the heat change, we will use the bomb calorimeter. Okay, and this reaction is carried out at constant volume. Okay, so the bomb calorimeter, okay, so this is what the bomb calorimeter looks like. Okay, so basically we have our vessel here, and then this is where the reaction occurs. So if you look down here, okay, at the sample cup, this is where the combustion happens. Okay, and then for this combustion, why do we call it a bomb calorimeter here? Because this is an insulated cup, this is an insulated container, and surrounded by the insulated container is water. Okay, so basically this is how your bomb calorimeter looks like. Okay, so the basic principle for our bomb calorimeter is the same as other thermochemistry. Okay, where we have heat release equal to heat absorbed. But for here, our heat release, it will be by release from combustion. So heat release by combustion, and the one that will absorb the heat release from the combustion or the reaction is either calorimeter or water. So if we talk about the calorimeter, okay, it refers to the bomb calorimeter here, this one, the small one down here. And then water is the water surrounding the bomb container. So this will be the equation that we're going to use. So for heat absorbed by water, we will use mc delta T, so mass of water, specific heat capacity of water, and also delta T, and calorimeter. For heat capacity, for heat absorbed by calorimeter, it will be the heat capacity of calorimeter times the delta T. Now, we're going to look on the calculation method involving the constant volume calorimeter. So based on the notes that I give you, we have two cases. Okay, the first case, the heat release. Okay, determine first who release heat and who will absorb the heat. For the first case, since this is a combustion reaction, so heat will be released by the reaction, so from the combustion, and heat absorbed only by the calorimeter. So we have our principle here, so heat released by combustion equals to heat absorbed by the calorimeter. Okay, so you can write this down as Q reaction equals to Q calorimeter. So for the Q calorimeter, if you can see here, the equation will be Q calorimeter delta T, and the Q reaction, the reaction refer to combustion, the one that we want to find. So our calculation will focus on this part. Okay, so this is the first case. The second case, okay, the heat is still being released by the combustion reaction, but right now the heat will be absorbed by water and also calorimeter. Okay, so heat released by combustion equals to heat absorbed by calorimeter plus heat absorbed by water. So we can write this down as Q reaction, okay, equals to Q calorimeter plus Q water. So for this one, the Q calorimeter, so this is the equation for the heat absorbed by calorimeter. So heat capacity of calorimeter times delta T, and then for water, the mass of water, specific heat capacity of water, and also delta T. And the value of specific heat capacity of water, like I mentioned before, if it is not given in your question, so you should find the value at your list of constant. Okay, now, so how do we know which equation we will use? Okay, is it the first case or the second case? Okay, for this one, we need to analyze the question and look at what information is given to you. And then after that, you can choose which equation is suitable. So now, let's take a look on an example question. So, example question on the constant volume calorimeter, or to be specific, this question will involve delta H combustion. Now, example number 1. A sample of sucrose with a mass of 1.32 gram is burned in a bomb calorimeter. So the question already gave you that we are using bomb calorimeter, and if let's say the question did not mention any type of calorimeter, so please focus on the type of reaction. So for this one, it's already said that it is burned, meaning it we are talking about combustion. Okay, the heat capacity of this calorimeter had been previously found to be 9.43 kilojoule per degree Celsius, and the temperature change from 25 degrees Celsius to 27.31 degrees Celsius. So calculate the heat of combustion of sucrose in kilojoule per mole. Okay, so let's take out the information that we have in this question. So the first one, the question says, okay, we have our sample, which is sucrose, and given the mass of sucrose is 1.32 gram. Okay, and then it is burned in a boom calorimeter. Next, the question gives us heat capacity. Okay, heat capacity of calorimeter. Meaning here, the information given over here, okay, this one, this is our C calorimeter. Okay. 9.43 kilojoule per degree Celsius is our C calorimeter. Okay, and then next, the question gives the temperature change from 25 to 27.31 degree Celsius. So, if you look here, we have increase in temperature. The final temperature is higher than the lower temperature, meaning here we have heat released. Okay, because by right, when we talk about heat of combustion, so if you look back at the definition of delta H combustion, so delta H combustion is heat change when 1 mole of substance is burned completely in excess oxygen. So that's the definition. So our focus here, we want to find what is the energy needed, what will be the energy released when 1 mole of sucrose is burned. Okay, so since this is delta H combustion, and by the definition, the delta H combustion is heat release. When you are writing down the delta H combustion, okay, let me write this down back. So, delta H combustion, your final answer, delta H combustion of sucrose, the value you must put negative, the value that we calculate, and it must be in kilojoule per mole. Okay, so for this question, the question already asks you the heat combustion in kilojoule per mole. But if, let's say, the question just mentioned, calculate the heat combustion of sucrose, and it doesn't mention the unit here, you still need to give your answer, your final answer, in kilojoule per mole. Why? Because that's based on the definition of delta H combustion. So now let's take a look on how to answer this question step by step. Okay, so this is our question, and this is the information that we have just now. So to solve this question, I will separate the calculation to 3 steps, and all of these 3 steps will be used for all the question involving calorimeter, okay, that have bomb calorimeter or simple calorimeter. So now let's take a look one by one. So before we go with these steps, let's take a look back at the information that we have over here. Okay, the first one, you need to make sure that the unit here, the unit for the heat capacity or specific heat capacity given, you need to make sure that the unit over here, it must be in joule per degree Celsius. So if given to you, like in this question, in kilojoule per degree Celsius, so let's change it to joule per degree Celsius. So the value will be here 9.43 times 10 to the power of 3 joule per degree Celsius. So that's the first one. The second one is we want to find the value of delta T. Okay, so if we look at the temperature change over here, we have increase in temperature, meaning there will be heat release. Okay, why this is important? Because when you know it is heat release, when we are writing down the delta H later, so it must be negative. You must put the negative sign. When we are doing the calculation, we will not get any negative value if you use my way of calculation. Okay, why? Because my delta T over here, like I mentioned in the previous video, I will always use the bigger temperature minus the smaller temperature, regardless of final or initial. Okay, so the delta T over here, it will be 27 0.31 minus 25. So our delta T will be 2.31 degrees Celsius. So this is the value that we're going to substitute inside our calculation later. Okay, now, so let's take a look one by one. So the first step that we're going to do, okay, we will find the number of mole. So the number of mole of the compound or the species under our investigation. Okay, so what do I mean by here? Okay, so from the question, what we want to find is heat combustion. Like I mentioned just now, heat of combustion is 1 mole of substance. Okay, 1 mole of substance burned completely. So what is our substance? So our substance over here is sucrose. So we need to find the number of mole of sucrose given, okay, inside the question. Okay, so if I can put the title, okay, so number 1, we find the mole of target. Okay, so now our target for this question is sucrose. Okay, so let's find number of mole of sucrose. So N sucrose, we have the mass. Okay, it will be number of mole of sucrose. The mass is 1.32 grams. Okay, 32 grams over its molar mass, which is okay, the molar mass, 342 gram per mole. Okay, we will have the number of mole of sucrose as 3.86 times 10 to the power of -3 mole. Okay, so now what does this number of mole mean? Okay, we burn 3.86 times 10 to the power of -3 mole sucrose, and the energy later that we will calculate, the energy is for this amount of sucrose. Okay, so this is the first step. Okay, now next, step number 2. Okay, so for step number 2, what we're going to do is we're going to find what is the value of heat released by reaction or the heat reaction. Okay, for this heat reaction, like I mentioned before, the principle that we're going to hold on is heat released, the value, the number of heat released is equal to heat absorbed. Okay, now, so for this question, the heat will be released by the combustion. Okay, so let me put this as heat release from combustion. Okay, and then for the heat absorbed, so just now when we generally look at the equation the calculation method, we have two different cases. Okay, for bomb calorimeter, we have either first Q reaction equals to Q calorimeter, or second Q reaction equals to Q calorimeter plus Q water. Okay, when are we going to use the first equation? When are we going to use the second equation? Okay, now, so for this one, look back at the information that you have. Okay, so for bomb calorimeter or for combustion, the Q calorimeter is a must. Calorimeter must be inside the equation. Okay, the one that is not compulsory or the one that can be in the equation or not based on data is the heat release by heat absorbed by water, QW over here. Okay, so from the information that we have here, there is no information at all about water. The mass of water is not given. The specific heat capacity of water, yes, we have that information, but we don't have the mass of water. Meaning, for this example 1, we will only use the first equation. So the only heat will be absorbed by calorimeter. Okay, so this will be the equation that we're going to use. So Q reaction equals to Q calorimeter. So for Q calorimeter, the equation will be just heat capacity of calorimeter and also delta T. Okay, and all of this value is already given to you from the information here. So heat capacity of calorimeter, okay, we're going to use this one. Like I mentioned before, it needs to be in joule per degree Celsius. So 9.43 times 10 to the power of 3 joule per degree Celsius, and then the delta T is this one. So 2.31 degree Celsius. So from here, we can find the Q reaction, or actually the Q for combustion. Okay, it will be equal to the value over here. Okay, so use your calculator and then find the answer. It will be 564.3. And about the unit, so let's take a look at the calculation here. So we cancel this per degree Celsius with degree Celsius. So we will have the unit as joule. Okay, so here you have the heat release for the reaction is 564.3 joule. So the heat release here, the one that we calculate just now over here, this corresponds to this number of mole. So when 3.86 times 10 to the power of -3 mole of sucrose is burned, 564.3 joule of energy is released. Okay, so have we answered our question? Not yet. Why? Because the question asks for heat of combustion, and again I tell you, heat of combustion is for 1 mole of compound completely burned. Okay, so we need to find what is the energy released for 1 mole of sucrose burned. So that will be our step number 3. So step number 3, okay, what we're going to do is we're going to find the delta H combustion. Okay, so for the delta H combustion, what you're going to do is you will do stoichiometry. Okay, what stoichiometry are you going to do over here? So you will write down your stoichiometry as 3.86 times 10 to the power of -3 mole of sucrose. Okay, this one, when it is burned, it will produce 564.3 joule of energy. Okay, I put here energy released. So since I want delta H combustion for 1 mole, so calculate for 1 mole. 1 mole of sucrose. Okay, so show your steps of calculation. So 564.3 times 1 over 3.86 times 10 to the power of -3. So you will get the energy release for 1 mole is 5643342 joule. Okay, this is the amount of energy release. Okay, please take note that I keep on writing down energy release just to remind you that later when writing down the delta H value, it must have negative value over here. Okay, and writing down the delta H combustion, so if you just write down your answer as this, you will not get the final mark for the final answer. because the final answer, it should be, so delta H combustion for sucrose, or you just put down delta H combustion, okay, in bracket sucrose, okay, equals to, must have first the negative sign. Why? Because energy release, and you need to make sure that you change this into kilojoule. Okay, so change it into kilojoule by dividing it by 1000. Okay, so the value will be negative 5643.34, sorry, 0.34 kilojoule per mole. Okay, so this will be your final answer. Okay, this is our final answer. So delta H combustion of sucrose equals to negative 5643.34 kilojoule per mole. So this is for example number 1. Okay, so this is question number 2. A bomb calorimeter contains 1.2 kilogram of water, and then an amount of 3.5 gram of quinine is burned in the calorimeter, and this caused the temperature to increase from 19 degrees Celsius to 28 degrees Celsius. So calculate first the energy release in kilojoule if the heat capacity of empty calorimeter is 3.43 kilojoule per degree Celsius, and then B, standard enthalpy of combustion. Okay, so for this question, okay, it's actually similar to the previous question. It's just that the question split into two parts. Part A, we need to find the energy release first, and then part B, the standard enthalpy combustion of quinine. Okay, so this is supposed to be off. So for this one, the standard enthalpy combustion, okay, please remember, when we have standard, meaning the reaction occurs, the combustion occur at standard condition, which is 1 atm pressure and 25 degrees Celsius. So now let's highlight the information that we have. So in this question, we are given the mass of water. Okay, so let's write this down. So this is mass water. Okay, mass of water. And then next, the question gives us the mass of quinine. So this is the compound, the target that we need to find. What is the heat of combustion of quinine? And then given to you the heat change over here. So we have increase in temperature, meaning energy is released. Okay, so with all the information that we have here, now let's take a look on how to solve this question. So our question and the information that we have just now. Okay, so for the mass, so you need to make sure if you have any mass inside your question, please change the mass first into gram. So here we have mass of water 1.2 kilogram. So it will be 1,200 grams. Okay, that's the first one. The next one is the delta T. So calculate the delta T. So 28, the bigger temperature, minus the smaller temperature. So our delta T is 9 degrees Celsius. So this is still a combustion reaction. Okay, so we will use Q reaction, and then we must use Q calorimeter. So this is, like I said, a must for combustion. The next thing is we are given the mass of water. Okay, so if you remember the structure of the bomb calorimeter, where the vessel, okay, the vessel for the combustion is surrounded by water. So that is the mass of water here, meaning the water that surrounds the vessel for the combustion reaction. So the water there can also absorb the heat released by the combustion. So that's why for this reaction, so Q reaction, or Q release, okay, Q release by reaction will be absorbed by calorimeter and also water. So this will be the equation that we will use later. Okay, but like I mentioned before, our three step, okay, is still the same. So our first step, okay, is to find the target mole. Okay, so I just write this down, mole for target. Okay, we are still doing delta H combustion, so we need to find what is the combustion for quinine, meaning we need to know what is the energy release when 1 mole of quinine is burned. Okay, but to find 1 mole, we need to use the information given. So first, find what is number of mole of quinine. Okay, so number of mole of quinine, the mass that we have, 3.50 grams over its molar mass, 108 gram per mole. So we have the number of mole of quinine that burn in this reaction is 0.0324 mole. Okay, so this is step number 1. Okay, so let me highlight the step here. Step number 1. Next, step number 2 is for us to find the Q reaction. Okay, so to find the Q reaction over here, so like I mentioned before, the principle that we hold is heat released equals to heat absorbed. So for this question, the heat is released by combustion, okay, since it's a combustion process, and the heat absorbed is by 2 things, like the one we determined just now. Okay, so there will be heat absorbed by calorimeter, and then another one we will have heat absorbed by water. Okay, by determining this, okay, heat absorbed by water. So the equation that we're going to use, so Q reaction equals to Q calorimeter plus Q water. So for Q calorimeter is our heat capacity of calorimeter, and then delta T plus Q water is mass of water times the specific heat capacity of water, and then delta T. Okay, so let's substitute all the information. So this is to answer part A. Okay, part A first. So the heat capacity of calorimeter is given as 3.43 kilojoule per degree Celsius. So like I mentioned before, the value, it must be in joule. Okay, so you will write down as 3.43 times 10 to the power of 3. Okay, so this is for the first part, times the delta T is 9. And here, the delta T for both calorimeter and water is the same because it's the same component, okay, which will have the same initial temperature and also the same final temperature. Okay, next, the mass of water. Okay, the mass of water is already given to you as 1.2 kilogram, which you have changed to gram, so 1,200 gram. The specific heat capacity of water, which will always be 4.18, and then the delta T, like I mentioned, is the same. Okay, substitute and then calculate your answer. So you will get the answer as 76014 joule. But the question asks for the energy release in kilojoule. So heat release or energy release is the same. Okay, So your final answer, heat release. So you will write down as 76.014 kilojoule. Okay, at this time and moment, it's still not per mole. Okay, why it is not per mole? Because this is the energy released when we burn 0.0324 mole of quinine. Okay, so for question part A, we will stop until here. Okay, only step 1 and then step 2. Now, let's move on to question B, standard enthalpy of combustion. Okay, standard enthalpy combustion of quinine. So, to answer this, we will proceed with part B, which is our number. Okay, we will proceed with step number 3, where we want to find delta H. But now, the delta H is not just delta H, is delta H not combustion. Why? Because like I mentioned, the question asks for standard. So standard must have not. So the same step that we did for example 1, which we need to find the value for 1 mole by stoichiometry. So let's write down the stoichiometry. Okay, the stoichiometry will be, if we burn 0.0324 mole of quinine, okay, the amount of energy release is 76.014 kilojoule. Yes, you can put the value of energy here in kilojoule. Okay, it is allowed. So this, let me write down as energy released. So we want to find for 1 mole of quinine, okay, how many energy will be released? So 76.014 times 1 over 0.0324. So you will get the answer here as 2346.11 kilojoule. Okay, energy release. Okay, so like I mentioned before, if you just stop until here, you will not get the final answer, because for the final answer, you must write down the delta H combustion. So write down like this. So delta H not combustion. So it must be delta H not combustion. Okay, and then quinine. So since it is a combustion reaction, energy release compulsory to put negative sign. So 2346.11 kilojoule per mole. So this will be the answer for part B. Okay, the next part of calculation, we're going to look for constant pressure calorimeter, or sometimes also called as simple calorimeter, or also a coffee cup calorimeter. Okay, so for constant pressure calorimeter, simple calorimeter, it is used to determine the heat change for neutralization reaction. Okay, meaning it is used for us to find what is the enthalpy of neutralization. So let's recall back what is the definition of enthalpy of neutralization. Okay, so it's heat released when 1 mole of water, H2O, is formed when acid reacts completely with base. Okay, so our target for neutralization is the energy release when 1 mole of water produced. Okay, so the reaction is carried out at a constant pressure. So how does our simple calorimeter looks like? Okay, so basically this is our simple calorimeter, or like I said before, we call as coffee cup calorimeter. So for this setup, we can do it in the lab easily by having a beaker. Okay, and then we have an outside layer over here that will act as an insulator. Usually we will use a styrofoam cup. Okay, and then the beaker as the reaction chamber, as the reaction vessel, and then we have a lid, and we put a stirrer and also a thermometer. Okay, so if you look here, the outer styrofoam cup insulate the reaction mixture from the surrounding. So it is assumed that there will be no heat lost to the surrounding. Okay, because the styrofoam keeps the heat inside. Okay, and then the heat released by the reaction is absorbed by the solution and the calorimeter. So if you look here, the heat released from the neutralization is absorbed by the solution. So what solution do I mean by this? Okay, when we react acid with base, we will get a salt solution, salt and water, which will give us the salt solution. So meaning the solution over here correspond to the salt solution. Okay, so the acid, this is like I mentioned before, the acid-base reaction forms salt and water is assumed to have, okay, the density, we assume the density of the salt solution same as density of water, which is 1 gram per mil. So that's why the specific heat capacity of the solution will also be the same as water, which is 4.18 joule per gram per degree Celsius. Okay, so this is the basic principle. It's still the same. Something release energy and something will absorb energy. So in this case, the one that release energy is the neutralization reaction, and then the one that absorb the energy will be our solution. Solution confirm, okay, will absorb because our product is a salt solution, and then the calorimeter. Okay, and there will be energy absorbed by the calorimeter if the question gives you information on the calorimeter. So this is the equation for heat absorbed by solution, mass of solution, specific heat capacity of solution, delta T. So like I mentioned, the C solution here, specific heat capacity of solution, we will take this value 4.18, okay, and then the heat absorbed by calorimeter, heat capacity of calorimeter, and also delta T. For the calculation method, for simple cup calorimeter, we also have two different cases. For the first case, we have the heat released by the reaction mixture, and the heat will be absorbed and must be absorbed by the solution. Okay, so for this one, the equation that we're going to use is Q reaction, which is from the heat released by the neutralization, and then heat absorbed by the solution. So Q solution. So for Q solution, you need to have the mass of solution, the specific heat capacity of solution, and delta T. Later, we're going to look how to find the mass of solution. So this is the first case. The second case is when you have the information on calorimeter. Okay, the question gives you the heat capacity of calorimeter. So if that information is given, so the equation that you will use, Q reaction, will be Q solution, okay, heat absorbed by solution plus heat absorbed by calorimeter. Okay, heat calorimeter. So the equation, if you look here, for the solution is mass of solution, specific heat capacity of solution, delta T, and then the heat capacity of calorimeter times the delta T. And the delta T for both solution and calorimeter is the same. Why? Because it's a same component. Okay, now, so let's take a look on example question. So I will provide you with two example questions for both cases. So now let's take a look at the first case. Okay, example 1. When a 25 ml of 0.4 molar HCl is mixed with 25 ml of 0.4 molar KOH in a coffee cup calorimeter, the temperature rose from 30 degrees Celsius to 32.7 degrees Celsius. So by assuming the specific heat capacity of solution is 4.18 joule per gram per degree Celsius and the density of solution is 1 gram per ml, determine the heat of neutralization. Okay, so let's highlight the important information from this question. So the first one, we have our reactant here, HCl and KOH. So given to us the concentration and also the volume for both HCl and KOH. Okay, next, the question gives us the change in temperature. So if you look here, the change in temperature, the temperature increase, meaning we have energy release. Okay, and if you look here, the question only gives us the specific heat capacity for the solution and also the density of solution. So why does this question give you the density of solution? Because inside the calculation for our heat, the term that we have is mass. So you need to change first from volume to mass by using the information of density. Okay, so let's look at the calculation. Okay, so for a neutralization reaction, always start with writing down the balanced chemical equation. Okay, why the balanced chemical equation is important? Because you need to make sure that the target here, our target for neutralization from the definition, which is 1 mole of water. So you need to make sure that here you have 1 mole of water. Okay, and then write down all the information that you have under each reactant. So like I did here, so volume, concentration for HCl, and also volume and concentration for KOH. So the delta T over here, let's calculate the delta T. So it will be 32.7 degrees Celsius, okay, minus 30 degrees Celsius. So our delta T is 2.7 degree Celsius. Okay, now, so you need to make sure and understand that this is our solution. So the volume of the solution will be the mixture of the two volume here, the 25 ml of HCl and 25 ml of KOH. So that's why the final volume of the solution will be 50 ml. And like from the equation, okay, we have Q solution, heat absorbed by the solution, and based on the equation, we need to have the mass of solution. Since here we have the volume of solution, so like I mentioned before, by using the information on density, okay, the question already gave you the information on density, so use that information for you to find what is the mass of the solution. So, since the density is 1 gram per ml, so the mass of solution will be 50 gram. Okay, after that, we will start calculating by using our 3-step calculation. So the first step is we need to find the mole of our target. So, our target right now, from the definition of neutralization, like I mentioned before, it's our H2O. So we need to find what is the number of mole of H2O. How are we going to find the number of mole of H2O? It will be based on our reactants. Okay, since we have two reactants here, what you need to do is you need to find what is the limiting reactant. So which one between HCl or KOH is the limiting reactant. Okay, now So let me write this down. Okay, so for our first step, I just write the first step here. Mole of target. So it will be slightly different from the one that we did for combustion. So to find the limiting reactant, find first the number of mole of HCl. So number of mole of HCl, since it's a solution, we're going to use MV over 1000. So the concentration of HCl given to us is 0.4. The volume is 25 ml, so over 1000. So the number of mole that we get for HCl is 0.01 mole. And the same calculation will be done for sodium hydroxide because we have the same information from for sodium hydroxide, which we will get 0.01 mole. Okay, now, so when we have the number of mole of our reactant, so determine which one is the limiting reactant. Okay, how? You still remember how to determine your limiting reactant? So look at the stoichiometry over here. So 1 mole of HCl will react with 1 mole of KOH. Okay, so 1 mole HCl will react with 1 mole KOH. And here, since the number of mole is the same, okay, meaning since both number of mole is the same and the stoichiometry is 1:1, so we can say that there is no limiting reactant and both of the acid and base will be completely consumed. Okay, with that we can say that the number of mole of our target, which is water, okay, will be the same as the number of mole of our reactants. Okay, so this will be the stoichiometry. 1 mole of HCl will react with 1 mole of KOH, and since the number of mole of both is the same, so it will produce 1 mole of H2O. So for this reaction, okay, the number of mole of H2O that will be produced, so I just take one of the reactants. So let's say I take 1 mole of HCl. The stoichiometry is 1:1 with H2O, so number of mole of H2O. So the question, we have 0.01 mole HCl, meaning the energy that we look on this reaction is the energy released when 0.01 mole of H2O is produced. So this is our target, 0.01 mole of H2O. Okay, now, so this is step number 1. So now step number 2 is for us to find the delta H reaction. Okay, so for the delta H reaction, the same thing that we did for combustion. Okay, we're going to find, we are sticking with our principle, which we need to find heat release. Okay, the value of heat release is equal to the value of heat absorbed. Okay, just we need to identify what release heat and what absorb heat. So in this reaction, the one that release heat is heat release by neutralization. Okay, and then heat is absorbed by, first, like I mentioned before, for neutralization, we must have, okay, this is compulsory, so heat absorbed by solution. Okay, and then when we look back at this at the question, there is no information at all on the heat capacity of calorimeter. So meaning the heat released by the neutralization reaction will only be absorbed by the solution. So Q reaction equals to Q solution. So the Q solution we will have the mass of solution, specific heat capacity of solution, and delta T. So the mass of solution is 50 gram, the one that we have converted from our volume. Okay, so put down 50 gram. Specific heat capacity of solution. So it's already given to you here as 4.18 joule per gram per degree Celsius. And if the question did not give you the specific heat capacity of solution, remember it is the same as water. Okay, so 4.18 joule per gram per degree Celsius. So I put the unit here just for you to see how the units are cancelled out. Okay, and then the delta T is 2.7. So 2.7. Okay, substitute all the value and then key in the value on your calculator. So you will get the energy released from this reaction is 564.3, and then the unit it will be, so gram will be cancelled out like this, per degree Celsius here with degree Celsius. So the unit that we will get over here is in joule. Okay, so please understand the value that we have over here is heat release when this much of water, okay, when 0.01 mole H2O produced. Okay, so what is the target that we want? We want to find delta H neutralization. So heat of neutralization, delta H neutralization, meaning we need to find the energy released when 1 mole of water is produced. Okay, so that's why for the third step, okay, so our third step is to find delta H neutralization. Oh, so pardon me, before I forget, this is not delta H, this is Q reaction. Okay, so let me highlight the title. So first, mole of target, and then Q reaction. Now, we want to find delta H neutralization. Okay, so for the delta H neutralization, the same step that we're going to use as what we did in the combustion, where we're going to do stoichiometry. Okay, so here the stoichiometry that we have, since we want to find for 1 mole of water, so the one that we calculate just now is for 0.01, so 0.01 mole of H2O. When 0.01 mole of H2O is produced, okay, 564.3 joule energy release. So to find for 1 mole, so write down 1 mole H2O. So do your calculation, 564.3 times 1 over 0.01. So we will get the energy release as 56430, and the unit will be joule because we start here with joule. So joule energy released. Okay, we are still not at our final answer. So the final answer you must write down as delta H neutralization, okay, equals to, since we have here heat release. Okay, why do we have heat release? Because the final temperature is higher than the initial temperature, meaning there is some heat released. So you must put your negative sign, so negative, and it must be in kilojoule. So change this to kilojoule. Okay, so it will be negative 56.43 kilojoule per mole. So this will be your answer. Delta H neutralization is negative 56.43 kilojoule per mole. Now let's look at the last example for this video. So, a matriculation student carried out an experiment involving a reaction between an acid and base as shown below. So, the question already gave you the chemical equation between ethanoic acid with sodium hydroxide. So, we have here our salt solution. Okay, now, in experiment, 20 ml of 2 molar sodium hydroxide solution was added to 30 ml of 1.0 molar of ethanoic acid solution in a styrofoam cup. Okay, so a maximum temperature rise of 5.8 degrees Celsius was observed, and given here the heat capacity of styrofoam cup. So if the question gave you information on styrofoam cup, if it mentions styrofoam cup, meaning it's your simple calorimeter. And the reaction here is your neutralization reaction. Okay, the question A, name the enthalpy for this reaction. Okay, so you will answer this as enthalpy of neutralization, or you can write down as delta H neutralization. Then B, calculate the standard enthalpy for this reaction. Okay, so let us just highlight the information that we have. So our base, okay, 20 ml of 2 molar sodium hydroxide, and then our acid, 30 ml of 1 molar ethanoic acid. Okay, and then the question gave us the delta T as 5.8, so we don't have to find the delta T, we just use the information given. And we have here the heat capacity of our calorimeter as 37.3 joule per degree Celsius. So now let's look on how to do part B. Okay? Okay. So this is the answer for A, enthalpy of neutralization, and these are the informations that we have for part B. So I already written down here the delta T, the heat capacity for calorimeter, and the volume of solution, which is 50 ml, where we get from the addition of the acid with the base, 50 ml. And since we assume that the density of solution is equal to 1 gram per ml, so we have the mass of solution as 50 gram. Okay. Since we are looking for delta H neutralization, so our target over here, okay, enthalpy of this reaction, which is neutralization, we need to look on 1 mole of H2O. So the same first step like the other examples where we find the mole for target. Okay, so mole for target. So now our target, okay, is we need to find the number of mole of H2O. So to find the number of mole of H2O, since we have two reactants here, our acid and our base, we need to find the number of mole of both. Okay, so let's start with the number of mole of our acid. Okay, we will use MV over 1000, so the concentration is 1. The volume is 30, and then over 1000, so we have the number of mole of our ethanoic acid as 0.03 moles, and then the number of mole of our base, sodium hydroxide. Okay, we have the concentration as 2 molar, and then the volume 20 ml, okay, over 1000. So we get the number of mole of sodium hydroxide as 0.04 mole. Okay, so right now you need to be very careful because the number of mole of the acid and the number of mole of the base is not the same. So since the number of moles are not the same, we need to find the limiting reactant. Okay, so how to find your limiting reactant? The same way as you always find the limiting reactant, compare the reactants. Okay, and do your stoichiometry. So if you look here, the stoichiometry between the acid and the base is 1 to 1, meaning 1 mole of acid CH3 COOH will react with 1 mole of NaOH. So since it is 1 to 1, so we can directly take the smaller number of mole as our limiting reactant, meaning this is our limiting reactant. Okay, the number of mole for the limiting reactant, meaning our acid here is limiting reactant, and then sodium hydroxide is excess reactant. Okay, why it is important for us to know what is the limiting reactant? Because we want to find the number of mole of our target, which is water. So to find the number of mole of water, we will do the stoichiometry of our limiting reactant, okay, which is acid. So 1 mole of acid will produce, okay, from the balance equation, 1 mole of H2O. So since the number of mole of limiting reactant is 0.03 mole, so the number of mole of water that will be produced from this reaction is 0.03 mole of H2O. Okay, so this is our start. Okay, this is our target. So the next step, step number 2, when we calculate the the heat release. Okay, the heat release from this reaction is when 0.03 mole of H2O is produced. So now let's move on with step 2. Okay, step 2, we want to find the heat from the reaction. So our principle here, heat release equals to heat absorbed. So heat release by neutralization. So since it is neutralization, okay, we will have heat absorbed by solution. So this is a must for neutralization. And at the same time, from the information, we have the information of heat capacity of calorimeter. Since we have that piece of information, okay, besides heat absorbed by solution, we will also have heat absorbed by calorimeter. So our equation right now will be Q reaction equals to Q solution plus Q calorimeter. So this will be the equation that we're going to use. So our Q solution is mass of solution, specific heat capacity of solution, delta T, and Q calorimeter is heat capacity of calorimeter and also delta T. So the delta T is the same for both solution and calorimeter. So now let's substitute all the information that we have. So mass of solution is this one, 50 gram. Specific heat capacity of solution, it's not given here, but we already know that the specific heat capacity is the same as water. So it will be 4.18, and then the delta T is 5.8. So this is for our solution, and then the for our calorimeter, so the heat capacity is 37.30. So make sure that the unit is in joule, okay, since it's already in joule, and then times by the delta T, 5.8. Okay, 5.8 over here. So you will get the heat released when 0.03 mole of H2O produced as 1428.54 joule. Okay, so like I mentioned before, the energy that we have here, this is for 0.03 mole H2O. So next, we proceed with our third step. Okay, so for the third step, is for us to find what is our delta H neutralization. Okay, so delta H neutralization, we need to find what is the value for 1 mole, what is the value of energy released when 1 mole of water is formed. So we will continue with our stoichiometry. Okay, so if 0.03 mole of H2O is produced, it will release 1428.54 joules of energy. So if we want 1 mole, so you do your calculation like always. So 1428.54 times 1 over 0.03. So you will get the energy release from this reaction as 47617 joule of energy released. Okay, so this is not your final answer. As your final answer, if you look back at the question, okay, the question asks for standard enthalpy for this reaction. So you need to write down the correct delta H. So delta H naught. If you just put delta H neutralization, it is wrong because it is not standard. For the reaction to be delta H to become standard, you must have the not sign here. So delta H neutralization. Okay, so since it is release heat, make sure you have your negative sign. So negative, and change this into kilojoule. So you will get negative 47.62 kilojoule per mole. So this will be our final answer. Okay, so that's it for example 2. So I hope you managed to understand the step-by-step calculation for both bomb calorimeter for combustion and also simple calorimeter for neutralization. Okay, so if you understand how to take out the information from the question and then choose the correct equation to use, there will be no problem for you to solve the question. And remember the 3 steps. First one, find the number of mole of the target. Okay, the second one, find the Q reaction, and last one, the delta H, either delta H combustion or delta H neutralization. Okay, so that will be the end for this video and also the end for subtopic 2.2 calorimetry. Okay, so that will be all for this video. Thank you for listening until the end. Bye.